So now we're going to look at what happens in a fibre reinforced composite when a crack propagates through it. So if we have the fibres arranged like this, and we're still dealing with the situation where we have a weak interface between the matrix and the fibre, so a crack will begin to run through the composite until it meets the interface with this fibre, and then it will run along the interface, and then maybe at some point it will find a weak point in the fibre, or maybe a fibre end. It will then propagate to the next fibre, and it might run in the other direction, and so on and so forth. What we're going to end up with is, rather than some failure like we'd have with a piece of glass that looks something like that, we're going to end up with something that looks much more like this, which is the kind of failure we expect with a tough material. So that's characteristic of a tough material, and that's characteristic of a brittle material. So it's to do with these interfaces between the fibres and the matrix. Now the problem is, if we have a really weak interface between the fibre and the matrix, we will apply a load to this composite, and it's the fibres that take the load rather than the matrix, and all that's going to happen is we're going to pull the fibres out of the matrix. So as far as load bearing capacity goes in the composite, it's completely useless. So in order to have a composite that operates effectively, we need to have a reinforcement coupling to a matrix with an interface that does have some bonding to the fibre surface. And that's the role of the hemicelluloses. And remembering back to some of the lectures where I was talking about the roles of the hemicelluloses and the structure of the hemicelluloses, if we were to look at the surface on a molecular scale of the microfibril, it has this sort of ridged appearance because that's the shape of the cellulose molecule. So the surface of the microfibril has a shape like that at a molecular level, and part of the hemicellulose molecule is able to bond with that with hydrogen bonding, and then we have another part of the hemicellulose that might adopt a different configuration, maybe a spiral, and that will then bond with the matrix, which is the lignin. So it's this region here in between the surface of the microfibril and this linear part of the hemicellulose, which controls the strength of the bond between the hemicellulose and the cellulose, the microfibril, and therefore it controls the bond strength between the matrix, which is the lignin, and the surface of the microfibril. So this is the region that is really important when we're trying to understand the properties of toughness, and also the properties of creep behaviour in wood, and also the properties of flexibility in wood. So this whole region here, which is mixed up with water, without the water we don't get these properties because the whole thing collapses in a process called hornification. This whole process will collapse down and become quite rigid. So without the presence of water, we don't get the flexibility, we don't get the toughness behaviour, and we do not get the creep behaviour of wood. So we have to take the toughness, which is a property that we want, and accept the fact that wood will also creep when it's under a constant applied load, and I'll talk about that in the next talk.